Okay, so we started the chapter of the Goldstein rings and thinking about the proportions of the material. I think I should call this injective modules in Goldstein rings because mostly in this chapter I think something like maybe 1/3, maybe a little bit more than 1/3 will be about something injective. So we briefly discussed basic properties of injective modules last time. Now I want to also briefly discuss injective cogenerators. And probably some of you already know everything about injective cogenerators, but I just want to formulate several statements, maybe prove some of them. So, definition. Well, first of all, we have a quite general definition of a cogenerator, say an object in any category. So, object, say E. Category C is called a cogenerator. If we have the following properties. So we have two maps, F and G, which are different, so F is not equal to G. These are morphisms in the category from some object X to some object Y. Then, for any such pair, so that if for any F and G was equal from X to Y, there is another map H from Y to the injective, to the cogenerator E, such that the compositions HF is not equal to the HG. Well, currently, we can say that the functor, so this definition is equivalent to saying that the functor HE, which is just another notation for the home in the category C, rank E, is faithful. Faithful functor. So proposition, again quite general. I'm not going to prove this. You can find this, I think, in any Google category theory, any Google category theory that covers a little bit more than just some very basic material. So suppose so let C be a category with products E in C is cogenerator if and only if for any object X in the category C there is monomorphism from the X to the E to the S. So let's focus on F. So you can embed this into some power of the cogenerator. Okay, but we actually won't going to use this definition of a cogenerator. I just want to relay this kind of general picture for any category with the definition that we're going to use in this course. I don't know, maybe this is a proposition, maybe a remark. Let's say this is a proposition, because well, it's quite simple. Object E, now in the category of modules, this is not really a commutative algebra statement. R in this case would be any ring, not necessarily commutative. So E is injective cogenerator, meaning that this is injective as a module and also a cogenerator. If and only if home over R from module M to the module E is non-zero for any modulo M which is itself not zero. So let's see how this definition is related to general definition. So this thing is something that you find in the category theory textbook, and this is how usually this thing is defined in the algebra textbook. So in one direction, if you know that this is injective object and the cogenerator in the sense that I defined above, well, in the additive setting, we can always take one map to be equal to the zero map. So now in this case, I'll take the identity map and I also take a zero map on the M. Right, these are two different maps. Hence, there is a map H. Oh, this is from M to M. So in this case, X and Y just equal to M. So from M to M, and by definition, there should be a map H from the M to the E, such that these two compositions are not equal, but one composition is zero and the other composition is just H. So H is not equal to zero. Hence, in this home, there is no zero element. So that's all we need to say in one direction. Now, in the other direction, in another direction is a little bit more, but still quite simple. So, yeah. So suppose we have this. So suppose this property about the homes is satisfied. So let's see. Again, I'm going to check this definition, but I'm going to take one of these maps FMG to be equal to zero. This is without loss of generality. I can do this. So if F is a map from M to N, and this map is not equal to zero, right? So I need to find another map H such that the composition is not equal to zero. Okay, well, I look at this map, I factor this into the canonical homomorphism to the image, and then I put this image into the M, right? So this image of F is not equal to zero, right? So maybe we take a non-zero map, so this is not equal to zero. Hence, since I know that for any non-zero module, there is a map from the module to the injective, to the object E, right? That is object we consider, right? So now this image is embedded into M, and this is injective, so there is an extension, right? And so let's call this extension H. That's exactly what we want, right? Because HF is not equal to zero. If you go like this, apply F first, then apply H. I can as well just by commutativity go like this. But this thing is an epimorphism, and this is non-zero, hence this composition is non-zero. The end. Okay. Just a general thing to relate one definition to another. Well, let me say the following, that in the category of the modules over Z, in other words, the abelian groups, Q mod Z is an injective cogenerator. Do you know how to prove this statement? Do I need to prove this? Oh, I know that you know.
We can check that home is not zero and extend it by generators of M.
Sure, yeah, that's exactly how you can do this. Well, it looks like everyone in the audience know how to prove it, so I'm not going to prove it say this is a little exercise. And of course from this we can immediately derive that the Hom over the integers from R to the Q mod Z is an injective cogenerator in the category of modules over R. And this is just one way to construct an injective cogenerator for any module. Notice that here I kind of treat R as a bimodule. Of course, this is an abelian group and also a module over R. So this Hom kind of use this abelian group structure, and then the result is of this whole Hom is just a right R module. If I consider this R as a left R module. Why this is an injective generator? Well, this is just a simple adjunction. If I look on the Hom over the ring R from M to this object that I just claimed to be an injective cogenerator, right? And then I apply the adjunction between Hom and tensor functor. I can rewrite this as a Hom over Z. Now here I'll keep M, but I'll need to take a tensor product over R with the R, which actually doesn't do anything. This is still M, right? And then what we have left is just Q mod Z. So you see that this Hom functor as a functor of the object M, well, this is faithful, right? Since this is faithful, so this is a cogenerator according to the first definition, and the first definition is equivalent to the second definition.
Could you, можете напомнить по-русски faithful, это что значит?
Строгий. Well, essentially, what you have here is the definition for this particular functor. Okay. And one, yeah. What's the kind of the upshot of what I'm saying here? If you look at this proposition and apply this to the situation of the modules, at least we know that any module can be embedded into injective module. This is why it easily follows from the existence of injective cogenerator, and that's something that we're going to use all the time in this chapter. Okay, one more proposition. An injective module E is a cogenerator if and only if it contains an isomorphic copy of each simple module. Yeah, so I'm continuing to assume that this is a general situation for any ring, not necessarily commutative. In the commutative rings, of course, instead of talking about simple modules, I can say that our modules are maximal ideal. These are all simple modules. Okay, so again, in one direction, this is relatively easy, right? So let's take S to be simple. Now we know that using this proposition, we know that for any module not zero, of course simple, and of course I assume that S is not equal to 0. We know that there is a non-zero element in the Hom, so there is F not equal to 0, which is a map from the S to E. But since this is simple, the kernel of F is 0, hence this is an embedding of a simple module into the injective module E. Okay, so if this is a cogenerator, it contains every simple module. Now in the other direction. Well, first of all, I claim it is enough to show this, to show that there is a non-zero f from C to E for any cyclic module C. Right? Well, that is because if you take any non-zero module, right, so you take a non-zero element, there is non-zero element in any non-zero module, consider the embedding, which is, so this is C. Now, since we have, for a cyclic module, we have non-zero map F to the E, then we can just take, since E is injective, we take the extension from this cyclic submodule to the module. So let's say F with a tilde. So if we know this, that this home is non-zero for any cyclic non-zero module, then we know that this home is non-zero for any module. Of course, assuming that module E is injective. That's what we use here. But for simple modules, this is easy. So, but for cyclic modules, this is easy. But any cyclic module has a simple quotient. And right, so we know that E contains any simple module, so we take this non-zero quotient to the simple module and embedding the simple module into the E. End of the proof.
It's because any ideal содержится в максимальном?
Well, you can say it like this, or you can say that, well, you take a cyclic module, you essentially just repeat the same argument with the Zorn's lemma and see that in any cyclic module there is a maximal submodule. Quotient by maximal submodule is a simple module.
Вот лемма.
Zorn's lemma. Yeah, and if you want, you can also generalize this a little bit and prove something like this. Any finitely generated module has a maximal submodule. That would be more or less the same argument. Okay. Definition. Yeah, so I just wanted to remind you, maybe before the definition, well, maybe let me say why I'm even saying this. Well, for example, I constructed one injective generator, kind of the standard categorical construction of an injective cogenerator, this thing, but also, for example, if you I still have to say this, it won't be exactly what I want to use later, but so if this is a local Noetherian ring, which will be the most interesting situation for us, then you can take K, which is R modulo M, and then you know that you can embed this into some injective module. Well, in some sense, you want to take the smallest possible such E. Then this E is an injective cogenerator of this category of modules over R, right? Because there is only one simple module, and we know that this simple module is inside E. So later we're going to develop the notion of injective envelope. So this will be just an injective module, injective envelope of the module K. Yes, and if you have more than one maximal ideal, and you still have a Noetherian situation, you can take a direct sum. And if this is not a Noetherian situation, you can take direct sum, but it's not necessarily injective, so you can take injective envelope one more time. So what I'm saying that by this proposition, we will get later another way to construct injective cogenerators, and in some sense, minimal injective cogenerators. And this is just some injective cogenerator, not necessarily minimal.
Do we suppose that E is injected here?
Yes, so this is the embedding of K into some injective module. Then any such injective module will be an injective cogenerator by the previous proposition. Okay, definition. definition of the injective dimension. Injective dimension of some module M. So is the number which I'm going to write like this for shortness ID of M over R. So this is the smallest integer n such that there is injective resolution. So we have M, embed this into I0, there's I1, done. So that's injective resolution. With the property that the I with the index M is equal to 0 for M greater than. Okay. So more or less the same definition as for projective dimension, but also you can define for flat dimension. So of course it's possible that the module has infinite dimensions, so you construct all possible resolutions and there are no resolutions with finitely many terms. Then you say that by definition injective dimension is infinite. And if it's possible to find finite injective resolution, finite length, then the smallest possible length is the injective dimension. Okay. Next proposition, quite standard. Oh no, well, before we do this, I want to say the following. So let R be an Artesian ring. M is an R module. S inside R multiplicative subset. As you can see, since I'm using multiplicative subsets, I'm assuming that R is commutative. Now this is commutative algebra statement. Before that, everything worked over any ring. So multiplicative subset, then injective dimension of the localization of the module is less or equal than the injective dimension of module M over R. Well, there's nothing really to prove here. If you just see the statement, everything is clear, right? Because, now first of all, to have a meaningful inequalities here, I'm assuming that this is a finite number, right? So there's a finite resolution. I just localize this resolution, and I'll get an injective resolution for this module. And since the localization of injective module for an Artesian ring is injective. So that's a very simple observation.
Why localization over material ring of injective is injective?
It was here last week. So that was the last proposition that I proved, that if you localize injective module on a Artesian ring, and this is still injective. That was quite simple computation. And I also say that there are counterexamples of non-Artesian rings. So we take polynomials over account of many variables. Okay, next proposition kind of standard for homological algebra, so and also easy. So this will be an exercise. Again, in this proposition, if you want, you can take a commutative ring. So let M be an R module. Then the following are equivalent. Three properties. First, I think we've done similar thing for the projective dimension. So injective dimension is bounded by the number n. Now assuming that there is a module and there's also some integer n, non-negative. 2. The x with the index n plus 1 between modules n and m is equal to 0. And this is true for any module, R module. And 3, x with the index n plus 1, but instead of in general n, you take r modulo I d o j. M is equal to 0, and this is for any ideal j in the R. Proof is that as an exercise. But that's really simple exercise. Okay. That's a general statement for any ring, not necessarily commutative. Now let's derive from this commutative statement. So let R be commutative Noetherian ring. M is an R module, and the following are equivalent. So first, the injective dimension of M is less or equal than N. 2, theXt with the index N plus 1 between R modulo P and M is 0, and this has to be true for any prime ideal. Proof. Well, of course, in one direction, if 1 implies 2 is trivial, so 1 implies 2. This is clear. There is nothing to prove. 2 implies 1. Well, do you see how you can prove that 2 implies 1 in the commutative case? Yeah, for example, if you want to use this, probably want to prove that we can, instead of R modulo P, we can plug in R modulo J for any ideal, right? But we can say about this module? At least we can say this is a finite module. So it's cyclic, but at least this is finite, right? But for any finite module over Noetherian ring, there is a prime filtration. And so use prime filtration R 1G. Right, so if you look at this filtration, if you know that for all such x are 0, you should just separate this into short exact sequences, and then step by step you'll see that all the terms in the filtration has trivial x, hence for R modulo J this is also trivial x. Oh, now we have something interesting, finally, probably the first non-trivial statement, and it won't be clear by this interesting statement. The reason is because we're going to use this several times in this chapter, so this is something like, maybe let me call this a lemma. Maybe you want to emphasize this lemma in your notes and call something like main technical lemma of the chapter, something like this. So let's take a local Noetherian ring. Let's take a prime ideal that sits inside M, but is not M, so it's smaller than M. So this is prime. And M is a finite R module. So then the statement is the following: if X with the index n plus 1 of the R modulo Q, second argument is M, is 0 for any prime ideal Q, so Q sits in the vanishing set of P minus P. Just a fancy way to write Q with another prime that contains P, but it's not equal to P. So then, from this vanishing I claim that there is a vanishing of the x with the index n for the R modulo P. Yeah. As I was saying, it's maybe not clear why this is an interesting statement, and maybe in its own right it's not a very interesting statement. It's interesting because it has many applications. And one of the first applications will be immediately after this lemma. And then there will be, I think, two more later in the chapter. Okay, is the statement clear? What's written here? Okay. Well, we take element x in the maximal ideal, but not in the prime ideal P. Well, this is possible because P is not equal to M, it's strictly contained in M. Look at the short exact sequence. R modulo P multiplication by x to the R modulo P, and there is some quotient R modulo ideal generated by the x and P, 0. Okay, now we can look at the long exact sequence of x for this thing, and then we will get x n R modulo Pm. Then there will be map induced by the multiplication on x to the x n R modulo Pm. Now my second argument is fixed, so I'm applying home, which is contravariant. X n plus 1 R modulo x p and still m. So this is the long exact sequence, well, kind of 3 terms from the long exact sequence. I'm going to need only these 3 terms. Okay, now the vanishing set of the ideal, if I want to write this property, I need double parentheses, so x and p. Right? So this will be all the prime ideals containing p and also containing x. X is not in p. So this is contained in the v of p minus p. Right? So this means if right, so this ideal has this containment. Well, it means that I'm just want to say that from this we can immediately see that the x for the n plus 1 R x p m is 0. Right? The argument is the same. Use prime filtration. Right, so for all primes containing this ideal, so all primes in the support, we know the vanishing by the assumption of the lemma, and then prime filtration gives us the vanishing of this x with the index n plus 1.
Yeah, in the lemma, then x n.
X n. Yeah. No, it's kind of interesting vanishing of x. Well, I find it convenient sometimes to read it in the other direction by saying something like, if you know that this xn is not equal to 0, then you can claim that the x with the index n plus 1 is not 0 for any q which is strictly larger than p.
Mm-hmm.
Okay, so this last claim is, again, by using prime filtration for the idea for this module. But then we're almost done, right? Then the last term is equal to 0. So multiplication of x is some endomorphism, right? So this will be an endomorphism of this xn, which is surjective. So I can say that the xn R modulo Pm is equal to the xn R modulo Pm. And applying Nakayama's lemma, we conclude the vanishing of the X and R modulo PM.
Why this text is finally generated?
Oh, we assume everything is finally generated, so M is finally generated, so all the X, this is clearly finally generated, so all the X are finally generated.
Why?
Well, I think the simplest way to see this, well, since this is finally generated, it has, this is the theory ring, remember, so it has resolution such that all the terms are finally generated 3 modules, right? Then if you start computing the homology, all the modules, boundaries, and cycles will be also finally generated. Okay. So maybe let me even call this the theorem, because it's an interesting statement. So as before, I assume that I have a local Artesian ring. And I have M finite R module. So then there's a formula. Injective dimension of M is equal to the supremum of the I such that xi between k and m is not equal to 0. Perhaps you recognize this set. What would be the number if I take the infimum instead of supremum?
The depth.
Yes. So, for example, depth is always bounded by the injective dimension. It's not a very interesting statement, we'll prove something better, but still, we get this for free. Okay, the proof is more or less clear if you just look at the lemma, apply the lemma, but the explanation of the proof may be not so easy, so let me try to do this. First of all, let me fix some notation. So let's say that the T is by definition this supremum that we have in this statement. Okay, well, first of all, clearly we have injective dimension of M is at least T. Right? This just always follows from the definition of T. Now, we want to show that there is inequality in the other direction. Well, first of all, I claim that for I greater than T, so I have x I k m is equal to 0, right? Now, the formal way to say this, I think something like this. By the descending induction on height, we will get xi r modulo pm is equal to 0 for any I greater or equal, greater than t, and for any p in respect r. Okay. So I have this vanishing, say this k, this is just r modulo, the maximum ideal. I want to get vanishing for any prime ideal, right? For example, let's first look we kind of know this. This is descending induction on the height, so the maximum possible height is for the maximal ideal, right? For the maximal ideal, we know this.
Mm.
So let's take prime ideal P of the height, which is maximum minus 1. So this is only contained in the maximal ideal. But this is for any I. For example, this is also, I want this for I, so I take this condition for I plus 1. Apply this technical lemma, and then I see that this is true for any prime ideal, so the height maximum minus 1. And then I just do this induction, and for each step of the descending induction, apply the lemma.
Can you repeat, please?
How we use lemma? Since in lemma we can't use the maximal ideal.
But for maximal ideal, I have this for free, right?
Yeah.
Just by definition of T.
Yes.
So now I'm trying to prove this not for the maximal ideal, but for the ideal of the height maximal height minus 1.
Mm-hmm.
Right? So then I need to check this thing. Right? But for height maximal minus 1, all possible elements here will be just maximal ideal. I already know this. I know this for any I. In particular, I know this for I plus 1. So for any I greater than T. Right? Is it better now? And then you just use this induction for, you know, this for height maximum minus 1, this for height maximum, etc. And now you see that you have this vanishing for any prime ideal, right? For any I greater than T, so you can as well just plug in here any module, and this gives you exactly the inequality in the other direction. End of the proof. So I think this is the first interesting statement. Okay. Yep. Try to somehow remember this lemma. I'm going to use this later, maybe even today. Okay, proposition. So let Rm be a non-Noetherian ring. M and N are modules. So if we take X in the maximal ideal, which is X in the maximal ideal R regular and also M regular, and additionally xn is 0, so on module n is acting as a 0. So then we have isomorphism of the X, so X with the index I plus 1 over the ring R, and M is isomorphic to the X with the index I over the R modulo X, and M modulo XM. Okay, now first there is, so this is for any I greater or equal than 0, but there is a kind of trivial remark how I consider N as a module over R modulo X, but X is acting trivially, so it's kind of naturally module over R modulo X. Proof. Well, first claim is that the functor hom over R from the R modulo X blank, this is a covariant functor from the modules over R to the modules over R modulo X transforms injective R modules to injective R modulo X modules. So it preserves the property of being injective.
Why is this property?
I'm going to give you a proof. Well, the reason is just simple Hom tensor and adjunction, right? I look at the functor Hom over R modulo X, say some test module T, and then I write Hom over R modulo X I. So I'm taking an injective module. I is an injective module over R. It's supposed to be R, not K. Right? So I want to show that this thing is injective over this ring. In other words, I want to show this functor, a kind of functor with a blank argument, is an exact functor, right? But this functor, by the adjunction, is the same as the Hom over R test module T, that's the product R modulo X with R modulo X I. Of course, this thing can be identified just with the T. But clearly this functor is exact since I is injective.
Isn't it should be Hom over R over X?
Where? Here?
Yeah.
No. So the outer Hom is the same as the inner Hom.
Mm-hmm.
Okay, so I is injective R module. Right. So if this functor is an exact functor, then this functor is an exact functor, so this Hom maps injective modules to exact injective modules. Okay, now let's take an injective resolution. So for shortness, I'm going to write all the time something like this. Instead of writing this whole injective resolution, it's I0, I1, etc., I'm going to write, say, I with a bullet and this kind of symbol for quasi-isomorphism. For me, this is just a standard notation for injective resolution.
So is it true for any module of R, like Hom, if M is some module of R, Hom from M to blank, it's take injective module and sends this to injective module?
No, but I'm using that this as a product, this is just identity functor.
So some like for any submarine. Okay.
No, I don't see a room for generalization in this situation because I need this tensor product to be identity. Okay, so let's take an injective resolution for module M over ring R, of course, and set J with the bullet, another complex, to be Hom over R. First argument is R modulo X, and then you apply this to this injective resolution. So we're applying the functor that we discussed before to this injective resolution. So this is complex of injectives. By what we proved before. Okay. So how about the cohomology of this complex? Can we compute this cohomology? Well, we just taking Hom, right, between this module and injective resolution of the module M. So the cohomology, of course, is just the X. So the cohomology isomorphic to the X between module R, module X, and M. But if you want to compute this cohomology explicitly, we can do this. Well, maybe I need an index, so let me call this is IH with the index I, and this is X with the index I. So I claim that this is M modulo XM if I is equal to 1, and 0 for I not equal to 1. How we can make such a claim? Do you see how to prove this?
You need to take projective resolution of R modulo X. It's just R modulo X, and then just home it to the M.
Right, so I can compute X. So now this is homomorphism. By computing this X with the injective resolution of M, I can just as well use the projective resolution of this module. And the projective resolution is quite simple. Right, this is the projective resolution. And if I take the home from this resolution into M, right? So X is still regular on M, so there will be no zero cohomology, but there will be first cohomology exactly the quotient of M by X.
Isn't it the zero cohomology?
No,
So it's the cohomology in the second R in this short exact sequence. Well,
Yes.
after homing with M,
mm-hmm.
isn't it?
Oh, if you well, we can do this, right? So we need to take home into M, right?
Yeah.
So then there will be
M.
M, and then there will be a map.
Ah, it's in another direction. Yeah. I forgot that this reversing.
So there will be no cohomology here since X is regular, and the cohomology here is exactly the quotient of the M by the image, so Xm. Okay. So now let's do computation. X I over the ring R modulo X between M and M modulo Xm. So this is isomorphic to the homology Hi over the home R modulo X N. Now I need the resolution for this M modulo Xm, and I constructed this J, which is almost the resolution except that it sits in the wrong degree. So let me shift this by 1, and now I get the resolution. So this is quasi-isomorphic. So now I can take this shift by 1 and pull it out and say that this is a homology with the index I plus 1 on R modulo X. And for J, I just plug in the formula that gives me the definition of the J. So this is 1 over R modulo X, I, and use the adjunction. So this is isomorphic to the Hi plus 1 over R, and then the product over R modulo X, the R modulo X, and the second argument is just I. Okay. And finally, this is of course, well again, I identified this first argument as just M, so what I have here is X, the index I plus 1 between N and M. Okay. Any questions about this last computation? Okay. If there are no questions, let me derive a corollary, which is an interesting statement. So I take as in the statement in this proposition, I take a local Noetherian ring, so that Rm be a local Noetherian ring. M is a finite R module. is M regular. Oh, as before, I want X to be in the maximal ideal, of course. So otherwise, it's not very interesting. X in the maximal ideal is M regular and R regular, as before. Then, by looking at this X and comparing this with the definition of the injective dimension, I can see that the injective dimension of the R modulo X of the module M modulo Xm is equal to the injective dimension of M minus 1. Okay. Just immediately follows from the characterization of the injective dimension in terms of X and this isomorphism. Okay, theorem. So let Rm be a local Noetherian ring. M is non-zero finite R module. So if injective dimension of the module M is finite, then we have the formula for the injective dimension. Remember, before we have a formula for the projective dimension in terms of the depth. Now we have a formula for injective dimension. So injective dimension of M is equal M is equal to the depth of the ring. So previous formula had a name, also on the Buchsbaum formula. I propose we call this bus formula. It's not the standard name in the literature, but it's nice to have some names for the statements if I want to refer to those statements later. And I think Bus was one of the persons who proved this formula, so maybe the first one, maybe one of the first. So proof. Let's fix some notation. So let's say that R is by definition injective dimension of M, and T is the depth of R. Just for shortness. Okay, if we take a prime ideal P which is contained in M but not equal to M, and we choose X to be an element in the maximal ideal but not in this prime ideal. We look at the short exact, sorry, not exactly short exact, this is only exact on the left. So look at this left exact thing. Then the functor X with the index R, remember that R is the injective dimension, so blank comma M is right exact. Do you see that this is right exact? Now you essentially just write the long exact sequence for the X and look at take any short exact sequence, right? Write the long exact sequence for the X and look at the very end where this X is stopping, if I have 0. Then you get exactly the statement that this R with the last non-zero index, right? Then this gives you the right exactness of the X. So this is a right exact, and hence applying this functor to this thing give me the following and exact on the right sequence: X R modulo P M map induced by the multiplication on X R modulo P M 0. So the same thing as we've seen before several times, and even today we have a This is clearly a finitely generated module, so X is endomorphism, surjectives, apply the Kayama's lemma, and conclude that the X R modulo P M is equal to 0. Okay, so we have this for any prime ideal, right, except the maximal ideal. Now, if we additionally assume that X R modulo M and the module large M is equal to 0, right? If this is true, now we have this claim just for any prime ideal in this spec. And it means that this X is vanishing for any first argument. So if this is vanishing for any first argument, then we can say that the injective dimension of M is less or equal than R. No, not exactly. This is not less or equal than R, but this is less than R, because X to the index R is vanishing for any first argument. But that is just not possible, right? R is the injective dimension, so that's a contradiction. So we know that the X R between K, let me just write K for the R modulo M, again for shortness of the notation, M is not equal to 0, okay? Because if it is 0, then we get a contradiction. All right, so now we know that the depth is T, so there is a maximal R sequence. So let X, which is X1, up to Xt in the maximal ideal, be a maximal R sequence. And just for shortness of the notation, I set N to be the quotient of the R modulo the ideal generated by this sequence. Okay. M is contained in the set of zero divisors of N. So this Z stands as usual for the zero divisors of the module N. Well, that's because we choose the maximal possible regular sequence. So there is no way to extend this by 1. So all other elements in the M are zero divisors of this module. Well, if M consists entirely of zero divisors, then M is associated to the module M. Or in other words, there is an embedding of the K into the module N. Yeah. So now applying this X with the index R, which is right exact to this thing, we will get X R and M X R K M. Right, so this is exact. And we know that this thing is not equal to 0 for a field. This is not 0, hence this is not equal to 0. For any, now not for any, now for this module N that we just defined. So this is not equal to 0. The Kazoo complex for this sequence, since this is a regular sequence, is a free resolution of N. now I can use this free resolution and compute with this free resolution x with the index t between m and some module m. So let me plug in little computation. So this is complex, of course, of length n. We have of length t. We have t elements in the regular sequence. So this x with the largest possible index will be proportional of the map home between the exterior power n minus 1 of the free module, the m generators, and m. This will be the dual map in the Kazoo complex. So let's call this d star with the sequence x to the home Rm, which is of course just m. So this thing, if you just remember the definition of the Kazoo complex, you can easily see that this can be identified with the quotient of the m by the xm. And I think we've done this computation before when we discussed Kazoo complex. So this thing is of course not equal to 0.
What is L2?
What?
What is L2?
There is no L little, this is t. Thank you. And this is also t. Right, so we have t elements, so this is Kazoo complex on a free module of rank t. Okay, so we use this Kazoo complex to compute this x with the index t, and we see that the answer is always non-zero, right? That is because this ideal generated by the sequence x sits inside the radical, m is finally generated, so by Nakayama's lemma this can be 0. No, I assume that m is not 0. We assume that, yeah, I said m is not equal to 0.
Can you repeat this? Can you repeat this?
I'm just saying, while computing this x, I'll get this quotient, more or less by computation with Kazoo complex. I'm saying that this quotient is never 0, because if this is 0, m is equal to the xm, x is sitting inside the maximal ideal, so it's inside radical in this case. So by Nakayama's lemma, this should mean that m is 0, but m is not 0. Okay, so that's all the computations that we need. Now we just need to carefully analyze what we get and see that the formula is correct. Well,
I suppose we also need to say that x with higher than t should be 0. Because,
yeah, but that's true because there are no terms in this complex. Yeah, but I just want to say that I can see a couple of inequalities. I can see that t is less or equal than r. Right? I see that this x with the index t is non-zero. So, and if I compute this x using the injective resolution, and I know the injective dimension of m is r, I need to say that t is less or equal than r. Otherwise, I'll get the contradiction. Right? So, let me say, this is by this computation. So, t is less or equal than r. This is what we get from this computation. Now, but I know, I've already proved this, x with the index r, prove it here, between m and m, is not equal to 0, right? So, t is at least r. And yeah, I know that this x with the index r is not 0, but I want to compute this x using the Kazoo resolution of n, right? And if I don't have enough t's, right, to get the complex of the right length, I'll get automatically 0 because there's nothing in the complex, nothing in the resolution. So it means that in the complex, I need at least r terms to get this x not 0.
Yeah, t less or equal than r, it seems just r is the injective dimension, yeah?
Yeah. So since r is in injective dimension and this x is not 0, it means that this number t has to be less than r, less or equal than r, because otherwise it's supposed to be 0 for any t greater than r. Yeah, and this is by looking at this kind of answer and trying to compute this answer in terms of the Kazoo resolution of n. Okay. If, for example, if this inequality is not satisfied, then the Kazoo resolution is just too short to get to the r, and we won't be able to get the non-zero text, because there is nothing, not just in homology, but there is nothing in the complex at this position. So just looking at these two inequalities, we finish the proof. Okay, so I think it's precisely time for one more statement, kind of the statement that goes together with the Bus formula. Well, one important formula, it's one of the main points of this course to prove this relation between projective dimensions and the depth, and adjective dimension and the depth. So one important formula, and this important formula has kind of a complementary inequality. So sometimes people combine this in one theorem. So I decided to separate them. So because the proofs kind of different. So again, let Rm be a local Noetherian ring. M is a finite R module. If the injective dimension of M is finite, then we have an equality. The dimension of M, meaning that this is just dimension of the support, is less or equal than the injective dimension of M. Okay, let P0, P1 up to Pd, which is equal to M. So be a maximal chain of primes in the support of M. So the goal is to show by induction, so we show by induction on I, which is just the index in this chain of prime ideals, that xi are localized at pi between residue field at the pi and M localized at the prime ideal pi is not equal to 0. Right, clearly if we can show this by induction, we prove this statement, right? Because if you know that such localizations are non-zero, we pull out the localization, and then we need to say that the x between something here and M is not equal to 0. So, and for any I which is up to the dimension, these are non-zero, so the injective dimension has to be higher than this number. So to this, if we can prove this by induction, we've done. Okay, based on the induction, if I is equal to 0, so then the P0 is the minimal prime in the support of the module M, and we know that the support and the associated primes have the same minimal elements. So I can claim that the P0 is actually associated with the module M. And localizing, I can say that the P0, RP0, is associated with the localization M at the P0. And if this is associated, I can say that the home over the localization R at P0 from the K P0 to the M localized at P0 is not equal to 0. So this finishes the proof of the base of the induction. Now let's do situation when I is positive. Let me, for shortness of the notation, just said that the B is the ring which is R localized at Pi. So then X with the index I minus 1 over the ring B, where you take B, you quotient by the Pi minus 1 B, just the extension of this ideal to the B, MPI, and then you localize this at the B I minus 1. Okay. So this thing is isomorphic to the X I minus 1. So over the localized ring, but I can write, so I need to localize B at the Pi minus 1, but this is the same thing as the R localized at the P with the index I minus 1. Now if I localize the first argument, I'll get K at the Pi, and of course the localization of the second argument is just the localization at the Pi minus 1. Okay. Do localization in 2 stages.
What's K in Pi? Isn't should be K in Pi minus 1? Like we factor it by Pi minus 1 and then localize it by Pi minus 1.
Yes.
So it should be Pi minus 1.
Wait, maybe. Just let me. Yeah, I think you're right. I think you're right. Yes, minus 1. So yeah, so this isomorphism is just the localization, the result of the we can apply localization to the ring and the both terms. Okay, now I can claim that this is not isomorphic to 0 by the induction hypothesis. So if I see the localization at the Pi minus 1 is not equal to 0, this is only possible if the module X with the index I minus 1 over B modulo Pi minus 1B and Pi. So this is not isomorphic to 0. There's this one localization which is not 0, then the module is not 0. So if this is not 0, then we X with the index I over P K Pi. Now this is indeed K of Pi MPI is not isomorphic to 0. And this finishes the proof. This implication.
Yeah.
This is what I call the main technical lemma of the chapter.
Yes.
If you read this correctly, if there is not vanishing, then there is not vanishing for the next X, which is precisely the next X, and also and also you go to the prime ideal, which is larger than Pi minus 1, so for prime ideal which is just Pi.
That's main technical lemma, but in another direction.
Yeah, well, it's the same statement, but can you read it in other directions? Okay, we have time? No, I think it's exactly time. Good. Let's take a 10 minutes break. Точно? Точно такое? Ну, если еще... А, это который 4, что ли, был? Ну, вот сейчас. У нас все ситуация такая простая. У нас здесь есть минус 1, да? На ним живет
просто в зуме, и там все сидели, смотрели.
с индексом I, да? Ну, как бы просто не стоит выбора. Вот если говорить, что существует, да, такой, да, вот это должен быть P, ну, потому что...
А вот еще что для этого?
Да? Нет, ну мы же на самом деле здесь везде рисовали, получается, у нас есть максимальный
позже.
Так, я не хотел, просто Ирина Александровна пропустила лекцию, чтобы гонять. Смотрите. Но я смотрю, я вам на почту написал, я онлайн, я что-то назвал онлайн, потом будет вас.
Да, там теперь новые правила, если она секунду просто на секунду просто добавили, все, ничего нельзя.
Вот, я на почту.
Ну, ладно.
Это я вам сразу больше не делаю, я извиняюсь.
Надо написать, что там были не один, там на самом деле еще парочку вопрос, который надо
Хорошо, да. Я думаю, я к вам здесь вернусь в скором, я же не досматриваю лекции. У меня 3 лекции впереди еще ничего не включает.
Я хотел спросить. У нас вот есть такая, ну, следствие, ну, что индуктивная размерность m, это индуктивная размерность m как поясен, плюс у нас там было написано минус. Нет, ну это индуктивная размерность m минус, это индуктивная размерность m. Да, ну это не принципиально. Вот, но вот здесь в этой лемме у нас как бы, вот, мы хотим считать с помощью вот этой леммы, ну, следствия. Вот, но у нас как бы модули над r, у которых, вот если x и плюс 1 m равно нулю, да, например, вот, но это значит, что там и плюс 1 это больше, чем негативная размерность, чем m. Ну, у нас же может быть так для всех n, у которых вот есть такое условие, но не для всех n просто.
Нет, когда нам ответить не надо. Смотрите, вы вот хотите посчитать, грубо говоря, вот это число. Да? И вы считаете его за счет того, что смотрите на текст.
Не, вот то, что почему оно меньше либо равно вот такого числа, это я понимаю. А вот почему другую сторону?
Я хочу просто равенство объяснить. Я не хочу вообще равно. Вот я хочу посчитать эту штуку. Да? Сейчас это, ну, грубо говоря, надо просто смотреть на эти тексты.
Ну да.
Я вообще не очень. Если я смотрю на эти тексты, и там у меня должен быть в этих текстах некоторые производные аргумент r, да?
Не, ну да. Там все n должны быть r по x модулем, да, это правда.
Да. Но это то же самое, что сказать, что n это модуль исходный, который x есть.
Ну да, нет, это правда. Вот. Сейчас еще небольшой момент с самого начала. Тут было такое утверждение, вот, что если e это модуль r, вот, и тут вы написали просто индуктивный когенератор. Тогда тут, да, когда геоморфизм экзамен e не равно нулю. Тут имеется в виду, что он индуктивный, и он когенератор, тогда это тогда. Ага, все понятно.
Нет, наверное, все-таки нет. Аккуратно нужно сказать так, что у вас есть индуктивный элемент, этот я предполагается индуктивным, это дано. Когда он когенератор, тогда это вот эти условия на полном выполнении.
Да.
Ну, я думаю, обязательно аккуратно сказал, потому что вот это.
А он сегодня лекция, кстати? Лекция.
Значит, введение дефективных генераторов.
Там, когда основной почему я рассказал, это что любой модуль, ну, жаль, то есть это сразу не может вкладываться в медицину. Что они медицину придадут, для этого мозга. Но я сейчас чуть-чуть скажу, как это существенное расширение.
Мы докажем теорему примитивные это ночь. Ну, то, что существа существуют.
Ну, по правде, некоторые из вас тоже знают.
Потому что был Homological,
Да, там доказывают произвольные категории.
Получается, индивидуальности всех модулей равны над локальным ключом.
еще могут быть бесконечны.
Или бесконечно.
Да. Ну, на самом деле, вот это вот существование я не сказал, но не имеет смысла сказать. Давайте я так вопрос там пока лекция не началась. Вот у меня есть, как обычно, локальное гиперокольцо и конечное порождение инъективной модуль над ним. Что вы можете сказать по поводу этого кольца?
Типа у него глубина 1 будет 0.
Не только, еще лучше могу сказать.
Еще лучше.
Let's do this exercise. Let me comment about these results. So suppose as before we have a local non-Therian ring. And say M is finite injective R module. Right? So then we can combine something that we know. We know that the injective dimension of this module is equal to the depth of the ring, right? But injective dimension is 0, right? And also we know that the dimension of the module is less or equal than the injective dimension. Alright. Now let me see, is this enough? Okay, let me say I want to show that this R is actually Artinian. So that not just the depth of R is equal to 0, but the dimension of R is also equal to 0. Well, I'm going to derive this from the bus formula and this inequality. Well, of course I know that I always have this, that the dimension of the depth okay. So what we have the depth of the module. This is bounded by the dimension of the module. This is bounded by the dimension of the ring. Maybe this is not enough. I think I can prove this quite easily that this module, that the ring is Artinian. Well, maybe not. Yeah, maybe this is not enough. Yeah. So, for example, if I say that R itself is injective, right? Then this will be R, this will be R. Then the dimension of R is less or equal than the depth of R. The reverse of inequality we always have. Then this will be a zero-dimensional coinequality. But if you just have this for some module, not the ring, I'm not sure that this is enough. So probably this is not enough. Okay, so for ring this works for module, I'm not sure. But there is a theorem, let me just maybe mention the theorem. Yeah, the theorem is that if you have a local Noetherian ring, and suppose you have a module, finally generated module of finite injective dimension, then the ring is coinequal.
What's the assumption of the ring?
Local Noetherian. Local Noetherian, and that means a module, finally generated module of finite injective dimension. Then the ring is necessarily coinequal. I think that's right. I hope I'm not
If
mistaken.
it's true, then the depth of R should be equal to the dimension of R. And
Yes.
then this will
Yes.
be Artinian.
Yes, that will be true, yes. But that theorem, it was the hypothesis of the bus, and it was altered for many years, and the proof of this is quite complicated, so we won't be able to do this in this course. No, we can do this in this course, but we need to sacrifice another material, and I don't want to do this. Okay, so now we go to another set of ideas, not exactly related to what I've done before. So this computation with the injective dimension, I'm going to need later when I discuss Wallenstein rings. But now I'm going to define the essential extension. So an essential extension, for shortness I'm going to write E. for essential extension of an R module n is module M such that n sits inside M and have the following property. So for any test submodule T inside M such that T is not equal to 0, intersection of the T and N is not equal to 0. Okay, remember? Let R be commutative Latvian. S inside R multiplicative subset. And suppose we have n inside M, a essential extension, then the localization of essential extension is essential extension. Okay. That's kind of one of the crucial observations. We're going to use this several times later. So, suppose we have x in the localization of the module M, and of course we assume that x is not 0. So what we want to show, and that will be enough to finish the proof, is to say that the localization of the ring X, it's just this cyclic module, intersection with the localization of M is not equal to 0. Right? If we can prove this, we can say this is essential extension. So essentially I'm doing this for cyclic modules, but if you know this for cyclic modules, you know this for all modules, because take a module, take an zero element, generate a cyclic module. Okay, so this is the goal. Well, first of all, kind of two reductions. First reduction is that without loss of generality, I can assume that this x that I consider is not in the localization of M, but in the M itself. Right, since I'm just interested in this intersection, so since for any x which is in the localization of the module, I can find y in the M such that localization of Rx is the same as localization of Ry. Right. So with this ring, I just multiply generated by the invertible element. Clearly, this is the same submodule. So without loss of generality, so if x is not an M, I replace this x by this y and work with the y. Let me call this again x. So this is the first reduction.
You mean, excuse me, y is in N? Or
Yeah. I'm just saying instead of working with some fraction, I can just work with a fraction is denominator 1. Well, because this for any x, right? I can multiply this by denominator and go to the y, and some modules are the same. You multiply by generating an invertible element. It's just if it was a generator, it's a generator of the same thing. Okay. Another reduction can be achieved as following. We consider the set of ideals. So the set of ideals. So of the annihilators of the Tx such that T is in the multiplicative set. Right? So this set of ideals has maximal element. Let's call this maximal element annihilator Sx. Right? Why the set has a maximal element?
Well, because R is not real.
Yeah, because I assume that R is not trivial. So any family of ideals has a maximal element. Yeah, so this the maximal element is just this SS analyte of SX is just my addition of the maximal element. Now look at the S inverse Rx and the S inverse RSX. I'm doing the same thing, I'm multiplying the generator by an invertible element. So they are still the same. So the second introduction is that without loss of generality, I can assume that the annihilator of the X is maximal in that set. Okay, so this is kind of two reductions, and now the proof. So we know that M inside M is the essential extension. So if I look at the Rx and cyclic submodule inside M Rx and intersect this with the M, well, first of all, I can notice that cyclic submodule inside M Rx and intersect B just some elements of the form something in the R times X, or something in the R form an ideal. Alright, so, and this is non-zero because it's an essential extension.
Why it is of such form? IX.
No, just a simple exercise in the sets. You try to write what you have here. Here you have something like little R times X, right?
Yes.
And you check that if you have little R times X there, you multiply this by other element, and it still will in the right form, so it will be an ideal. Petitions form an ideal. Okay, so for this ideal, since the ring is Noetherian, I can choose generators. So let me write that this ideal generated by some A1, A2 up to some AM. Okay, so if generator AI times X is equal to 0 in the localization, so in S inverse M, so I want this to be for all I between 1 and n. So if all these things in the localization are 0, then there is element T in the multiplicative set S such that T AI X is 0, but now not just in the S inverse M, but in the M. Okay? So if you have this, as usual, if you have an element which is 0 as a fraction, it means that you can multiply this, say, this individual thing by some Ti, such that this product is 0 in M, and then this T is just product of all these Ti's. So again, here, this I, the index that we have here is between 1 and n. Okay. So in other words, we can say that if I look at the element Tx, right, so Tx is annihilated by all these AIs for any I. Right, so Tx is annihilated by all these elements, or another way to formulate this, I can say that the I
lies in
maybe I say it like this. Well, first of all, annihilator of the X is the same as the annihilator of the Tx, right?
Why do I need this?
This is by maximality. Well, I have this.
I would have this.
by maximality.
Isn't it should be consistent? Annihilator of Tx should lie in annihilator of x. This maximal in this set. So it's maximal ideal by включение.
Sure, and the other inclusion is also true.
Ah, yeah, that's true.
So and then we have this annihilator of x, the same as annihilator of the Tx, right? So all these AIs annihilating Ti's, hence all these AIs are annihilating x. So this is for any I between 1 up to n, right? So it means that Ix is equal to 0, which is a contradiction with the fact that we have an essential extension Nm. Hence, what we can conclude from this is that there is an index I such that Aix is not equal to 0 in this localization. And so the intersection of the S inverse Rx intersect with the S inverse N is not equal to 0. Okay. So this is a little lemma. So okay, now another property which is quite general. Again, not necessarily about commutative rings. It says that a module N is injective. Module N is injective if and only if it has no proper essential extensions. Proper meaning that when you consider extensions, say n, you embed this into m, this m has to be different from n. Of course, we always have such an essential extensions when n is just equal to m. Okay, so in one direction, so assume that this is injective, right? So the assumption is n is injective. I want to show that there are no proper essential extensions of injective modules. So let's take an extension, so n inside m. Well, first of all, m is isomorphic to the n plus the complement, right?
Yeah, can I ask quickly? Has no proper extensions. Essential extensions means that if we have, if n is have essential extension in m, then m is equal to n.
Yes, exactly. Yeah. So I take an injective module. I take any extension. I claim that this extension m is necessarily a direct sum of n and some complement c. Well, this is just because this is injective, right? One of the characterization of injective. So if you take a short exact sequence, here it will be n embedded into m, and there is a quotient which is c. This is supposed to be a splitting sequence. So m is isomorphic to a direct sum. Okay. Now, so we have this isomorphism, and n intersect with C is 0. No, that's a direct sum, right? Direct sum of two submodules. And since we assume that this is essential extension, right? If I say this is essential extension, I can conclude that C is isomorphic to 0. And if C is isomorphic to 0, it means that the M is just, it's not just isomorphic, they coincide. N is the same as M. So there is a submodule and they have to be isomorphic. It's only possible when they coincide. So that's the whole proof in one direction. In the other direction is more interesting. So let's consider a situation where I have some monomorphism between modules u and v, so call this monomorphism phi. And so I know that n has no proper essential extensions. I want to show that I can do the extension. So I want to show that for any map, say alpha from u to the n has extension to the v. Right? So this is what we want to show that this module n is injective. We just check more or less the definition. I take any map to this injective to the module, and I need to find an extension from the u to the v such that the corresponding triangle will be commutative. Okay, to do this, I consider a push-out diagram. So I have u, this is map phi to the v. So now I have this map which I called alpha to the n, and take a push-out. Let me denote push-out by w, but this is just a short notation for the push-out of the v and n over the u. So a general property of the, let's call this map psi. So the general property of the push-out is that if you take a push-out of a monomorphism, you'll get a monomorphism. So map psi is a monomorphism. If you don't know this property, you can check this. You can do this in, say, a Abelian category abstractly, or you can just do this concretely for modules. Okay, now I want to apply this Gauss lemma. So by Gauss lemma, there is maximal submodule D inside module W such that n intersect with D is 0. So the map from the n to the W modulo D is an essential extension by construction. And we know that n doesn't have any proper essential extensions. So we conclude that the n is isomorphic to the W modulo D. And notice that the intersection of the n and d is 0. So we can say that the W is the isomorphic to a direct sum of the n plus d. So the extension that we're looking for, the extension of alpha, is just the composition of the projection to the n with the map gamma, where gamma on this diagram is this map. Right? So gamma goes to the W, so W is isomorphic to the sum of two things, and then from the W you just apply projection to the first sum of the two. And it's quite easy exercise to check this. Actually, this is an extension, meaning that, so here we have, no, there's a map projection here. So if you go apply gamma and apply projection, then it will be exactly the same thing. So there will be a map like this. So if you combine this with the phi and go phi, gamma, and projection, this is precisely alpha. So that's the extension.
Well, just since when we combine it with psi, it will be equal and psi is mono. Yeah. So these two maps?
Yes, yes. Or you're just saying that what's called this projection is the section of size section of the projection or something like I'm sorry for this.
So I suppose size should be actually.
Yes, size sections. Okay. So this is one way to characterize an injective module. It has no proper essential extensions. We will need this essentially in the next proposition, I think. So first let me give a definition. An injective hull of a module M is an injective module E such that we can embed this M into this E and this map is an essential extension. So notation, well, I'm going to write E R of M for an injective hull. Maybe it's a little bit too early for the notation because, well, this can be any injective module right with this property. And we're going to show that such modules unique up to isomorphism. So construction is not canonical, but at least this is unique. So notation makes sense up to isomorphism. Okay, proposition. So, yeah, everything is quite general at this moment. It's not necessarily commutative. So but the goal is to show that over any ring, any module has an injective hull. And this injective hull is, in some sense, is the minimal possible injective module that contains the given module. So you can proceed with this, construct the minimal injective resolution that has nice properties. So that's the goal. So let M and I be our modules. I assume that M is embedded into I, and I also assume that I is injective. So then, maximal essential extension of M in I is an injective hull of M. So in particular, I know that if I start with any module, because I have injective cogenerators, I can always embed the module into some injective module, and then I just choose the maximal essential extension inside this module E, and this will be injective hull. So in particular, from this it follows that any module has an injective hull.
What is Russian equivalence of injective hull?
Okay, so the proof is again some application of the Zorn's lemma. So there are, if you do this abstract constructions about injective hulls, there are several applications of the Zorn's lemma. So in the set, which I'm going to call S, which is just all modules N, such that M sits inside N if the extension is proper, and N is contained inside the given injective module I. So we have this, and let me emphasize that the M inside N, this is proper essential extension. Okay, the duplicating is not in the notation, and also writing that this is proper. Okay, so we consider this set and apply Zorn's lemma. So, as usual, Zorn's lemma. Applies.
Why is it not empty?
Why this is not empty?
Yeah.
That's a good question. I actually haven't thought why this is a non-empty set.
I think you don't need that m not equal to n. It will be equal, and then s.
So that is clearly non-empty, but
But why we need this?
well.
Why is clearly not non-empty?
If m not equal, если мы уберем, короче, утверждение, что m не равно n, тогда m.
А не может быть разве такого, что один индуктивный модуль вкладывается в другой?
Sure.
Yeah, there is a possibility of m is already injective, right? It is embedded, so its injective value is just m.
Yes.
So maybe I need to remove that this is proper.
Mhm.
And then this is clear that this is non-empty. Okay, so then Gauss lemma tells us that there is a maximal element. So let's call this maximal element E. So then we have a situation where M is contained in the E, maximal element E. And E is contained in the given injective module I. Okay. So I want to show that E is injective, right? But to show this by the previous proposition, it is enough to show, so we want to show that E has no proper essential extensions. Okay. So suppose we have one. So if E is contained in the E prime, this proper essential extension, well, then what we have this, I think we have E inside E prime, right? And then I know that E can be, it is embedded by construction into the injective module I, so I can do the extension and extend this map to the E prime, and let me call this extension psi. And then I just look at the possible situations. So if kernel of the psi is equal to 0, then I have M inside the image of psi, which is the same thing as the E prime, so is a proper essential extension of M in the injective module I. And that is not possible, right, because we choose a maximal element. So that's a contradiction.
Who is M?
Hmm?
Who is yeah.
M is something that we have in the statement.
Why should M?
Yeah, so maybe a little non-trivial thing to notice here, that M is sitting inside E, which is essential extension, E sitting inside E prime, which is essential extension, but the composition of two essential extensions is essential extension. So this is why I have a contradiction. And the second case, if I have kernel of the psi not equal to 0, so in this case I also want to get the contradiction. Well, since E inside E prime is essential extension, the kernel of the psi intersect with the E is non-zero. But what is this kernel of the psi intersect with the E? Well, that is precisely, by looking at the diagram, the kernel of the map from the E to the I, right? So this map. But this is 0. we know that E is a submodule inside I. So that's again another contradiction. And that's the end of the proof. Okay. Corollary, which is more or less proved by the same computation with the kernels, so I'm going to leave this as an exercise. So let me say that in the setting of the proposition, meaning that I have a ring, two modules, and one is embedded into another, there is monomorphism, let's say phi, from the injective hull of M into I. If you just construct it, right? We constructed this submodule, right? Which is an injective hull. So let's call this embedding phi.
Why E is injective in the previous proposition? We have shown that
It has no proper extensions. Hence, this is injective by the propositions before. Okay. So we have this mono, which is an injective hull of M embedded into I. And the diagram is commutative. And diagram, well, we have M embedded into injective hull and M also embedded into I. We know that this can be embedded, so this is phi.
Что такое E как M?
This is an injective hull that we constructed in the proposition.
It is by construction.
No,
Это же по построению внутри I.
yep, that's right.
А в чем тогда утверждение следствия?
А мы же пока ничего конечно, не сказали, ничего.
Yeah, so I'm just
sorry.
formulating
Excuse me.
what I have. Yeah, so I have this monomorphism, and the diagram is commutative. Well, I assume you agree that the diagram is commutative by construction. And in particular, U of M is a direct summand of pi. So you can see that in this sense, this is the minimal injective module containing the given module, right? You start with any I containing it, and then you construct an injective hull, and this injective hull is a direct summand. So
It's
there,
still not obvious why if we take just, another I, we still get the same E of M.
sure, at least we constructed one.
Mm-hmm.
This is what we have at the moment. Yeah, well, so the proof that in particular this is direct summand, well, since this is injective, all you need to show that this map is a monomorphism. The proof is more or less the same, so I'm not going to do this exercise. So, second corollary, if E of M and some E prime of M are injective hulls of M. Well, suppose we have two different constructions. Then there is isomorphism. So if I from the E of M to the E prime of M such that the diagram where you have M, you can embed this into the E of M, you can embed this into the E prime of M, and then there is an isomorphism phi such that the diagram is commutative. Now No, I want to say that the proof is clear by what we know. Yeah. Basically, first of all, so this is in particular M is embedded into injective module, right? So you take this. Well, you take this. You know that this injective hull, first one, it is possible to embed this as a direct summand into this injective hull, right? So there is also a map in the other direction by the same reasoning. And this maps in the both directions given the fact that this phi is an isomorphism. So just think about this. This is not really some algebraic computation, it's more like a categorical little observation. Okay, so indeed it makes sense to use this notation for injective hull. It's not canonical but unique up to isomorphism.
Excuse me, so we have that phi is mono and the image is direct summoned, but how does it mean that it is isomorphism?
Well, because you do this for the E of M, you can do exactly the same argument with the E prime of M.
Yeah, and why?
And then just look at the diagram. If this thing has to be a direct summand of this thing, and this thing has to be a direct summand of this thing, the only possibility is they're just isomorphic. Okay.
Что значит? Это значит, что если мы выводимся и потом реализуемся, мы не можем это identity.
Let's take a commutative notation.
Просто непонятно, что этот фи, оно может быть не низ, и вот если мы делаем такой фи, такой пси, то почему в композиции тогда не делаем?
Потому что фи уже предложение самого.
So we take a multiplicative set, and we take an M to be in our module. So then, if you localize the injective hull, this will be isomorphic to the injective hull of the localization of the module over the localization of the vector. Well, first of all, we already know that if we localize
Это просто из свойств essential extensions.
So if we localize an essential extension, right, so that M into the injective hull is an essential extension, we take localization, this is again an essential extension. We prove this never. And we also know that localization of injective module is injective. So this thing is injective. So it's essential extension and the second module is injective. So this thing is exactly the injective hull of this module. But the injective hull is unique after isomorphism, so it has to be isomorphic to this thing. Okay. So theorem, let R be in the Therian ring. Then I have two claims. First, that the injective hull of the R modular prime ideal is indecomposable. So for any prime ideal in the ring R. And the second, so if I is injective R module and the prime ideal P is associated to this injective module I, then injective hull of the R modular P is a direct summand of So in particular, all indecomposable injectives are of the form injective half of the R modulo P. So this kind of the beginning of the structure theory for the injective modules of Noetherian rings.
Извините, а что вот это слово после all?
Indecomposable.
Индек.
Indecomposable.
Что они не представляют себе прямой суммы. А это правда, что если у нас инъективный модуль, и он представлен в виде прямой суммы, и один из них инъективен, то второй тоже инъективен?
Mhm.
А то, что просто оба инъективны всегда, это верно?
Direct summand of injective is injective, yes.
Не, если инъективный представлен в виде прямой суммы каких-то двух, то они не обязательно инъективны.
No, I'm saying direct summand of injective is injective.
А,
Нет, вы другое говорите. Это вопрос про то, что подмодуль инъективного и инъективного. Это не всегда так.
No, you decompose an injective module into direct sum of two, right?
yeah.
Then both summands are injective modules.
Да.
No, just to look, for example, at the exactness of the home, where you fix the second argument. This is sum of two functors home for the first argument plus another argument. So if this is exact if and only if each of these two functors is exact. Or look at the x1. It decomposes as a sum of two x1s. No, it's very simple property. Yeah, so I think it's quite an interesting and important result. Well, at least we classify explicitly all the indecomposable injective modules. And of course, the second important theorem will be that if you have any injective module, then in a unique way, this is a direct sum of injective modules of this form. So it's kind of elementary building blocks, and every injective module can be constructed from these blocks by taking direct sums. But let's first prove this theorem. Okay, so first I need to show that this is indecomposable. Well, suppose this is decomposable. So if injective hull of the R modulo P is decomposable, so in particular I can claim that there are two modules, N1 and N2, inside the injective hull of the R modulo P. Of course, I want them to be non-zero, so N1 is not equal to 0 and N2 is not equal to 0, such that the intersection of the N1 and N2 is 0. Okay, so then we have the following observation. So intersection of the N1 and R modulo P, let's take first this intersection and intersect with the same thing but for N2. Well, this intersection of three modules, I can as well write this as an intersection of the N1 and N2, and then I intersect with the R modulo prime ideal P. Well, here I can say that this is non-zero module and this is non-zero module, right? That is because the extension from the R modulo P to the injective hull is the essential extension. So these two intersections are non-zero, and this thing is of course zero, right? Because this intersection by assumption is zero. So we can take some x and y. So x lives in the N1 intersect with the R modulo P. X is not equal to 0. And the same for y. So y is an element in the N2 intersect R modulo P. And y is not equal to 0. Well, if I look at the product x and y, then the product is definitely in the in this intersection. So the product being in the intersection of the N1 and 2 intersect with R modulo P, product is 0. But that's a contradiction with the fact that R modulo P is a domain. I constructed some element in particular that lives in this R modulo P, y lives in R modulo P. There are two non-zero elements, but the product is 0. What? R modulo P is a domain. So that's the proof of the first part. Okay, now let's look at the second part. So here I have an injective module and I have a prime ideal associated to this injective module. But I can as well just write this given fact as the existence of such monomorphism. Right? And if I can embed R modulo P in, sorry, not MI, injective module I. Right? But then it means that I can take injective hull and also can embed this into the given injective module I by the same argument as in the previous propositions. So if we have P associated to the I, we can embed injective hull, and since this is injective, it splits as a direct summand. So that's the proof of this theorem. Okay, so next theorem. So now I assume that R is Noetherian ring. So I have prime ideals in the spec of R spec. Spec of R and finite module. Finite R module. So then again, two statements. So first is that the set of associated primes of M is the same as the set of the associated primes of the injective hull of M. And the second statement is that the injective hull of the R modulo Q is isomorphic to the injective hull of the R modulo P if and only if these are the same two prime ideals. Well, what we can extract, for example, from this theorem, for example, another way to define associated primes. You take a module, take its injective hull, and decompose this into indecomposables, so it will be something of this form. And you see some list of prime ideals. This list of prime ideals is precisely the list of associated primes.
Why can be decomposed in
Well, we will prove this later. But if you believe in this, I'm just saying that you can read this set of associated primes precisely as a set of associated primes you see in the decomposition of this thing into the direct sum of such things. And in this way, you can generalize a theory of associated primes from the commutative algebra to non-commutative algebra. There are analogs of all these statements in the non-commutative case. You need to be a little bit more accurate. For example, atomic motion by prime ideal motion, say by electric reducible ideal, but it can be done. And in this sense, you can generalize associated primes to non-commutative situation. Okay, so let's prove this.
Если мы возьмем в качестве RZ, то понятно, что такое будет E от Z фактор pp.
Sure. Very, very easy and nice answer. Maybe we'll do some seminar, but probably. If you won't do seminars, it will be a problem with the assignment to me. precisely compute all the injective crossovers. Okay, so to prove one, what we know, well, since M is a submodule in the injective hull of M, by the general property of the associated primes, at least we can say that the associated primes of M are contained in the associated primes of the U of M. This is something that we get more or less automatically. Now, let's take associated prime Q, so associated to the injective hull of M. So, if this is associated, it means that there is a module, let me call this U, which is of course isomorphic to the power module of Q, and this module U is embedded into the injective hull of M. So U intersect with the M is not zero, right? Well, that is because M to the injective hull of M is essential extension. So this intersection is not zero. Now, again, we have a situation, we have some module, so associated primes of the U intersect with M sits inside the associated primes of the U. Right? That would be a submodule of the U, we have this. But U is this very nice, simply constructed module. And if you don't know this, you check this as an exercise. I think it's in the notes of the commutative algebra, that the associated primes for R module Q is just a set with one element, and this element is Q. So U intersect this M is not a zero module, so the set of the associated primes is not empty. So we have a non-empty subset into singleton. So the only possibility is that the associated primes of the U intersect this M is just this set with a single element. So Q that was associated to the injective hull now is associated to the U intersect this M, but again, this is inside associated inside M. And that's the end of the proof. Right? I started with any Q associated to the injective hull. I notice that this is associated to the U intersect M, which is a subset in the associated of M. So Q is associated to the M.
The second one is following from that it will have different sets of associated.
Well, let me just write a long and almost trivial formula, but from this formula was immediately the proof. So this is how I would like to do it. Of course, this is essentially stated in one direction. If P is equal to Q, clearly this is isomorphic, so we need to assume that we have such isomorphism and we want to show that P is equal to Q, right? But then I'll do it like this. So set that consists of one element, which is P. This is associated primes to the R module P. But what we just proved, we know that this coincides with the associated primes of the injective hull of the R module P. And this is the same thing as the associated primes of the R module Q. And this is the same thing as the associated primes of the R module Q, which is okay. Just a very simple proof when you know what. Okay. So now I need a lemma for the next theorem. In the lemma, I have let R be the theory ring. I have a prime ideal. Then residue field is isomorphic to the home over localization from the residue field to the injective hull of the R modulo P localized at P. So in some sense I can compute this home, and this home, which is clearly a vector space over K of P, is just one-dimensional vector space over K of P. Well, the proof is the following. Since we know that the localization of the injective hull is the same thing as the injective hull over the localization, right, so we can as well just do this computation for the local ring. So R is R localized at P, and this P is just the maximal ideal. And of course K, for shortness, it will be R modulo M. So we can reduce everything to the local situation. Now we look at the vector space as well. First of all, this is home. So B is the home over R from K to the injective hull of K. Well, we can equivalently write this as the set of OX in the injective hull of the K such that M annihilates this X. Very easy observation. I think we already used this. How we get a home from the K, which is generated by one element, to this module. Well, we just take any element which is annihilated by the maximal ideal. Well, inside this V, we of course have. Well, first of all, we can notice that this is just a vector space over K. And of course, we have a K inside, so that's not a zero vector space. Well, that is because, well, K is always mapped to this injective hull. So if there is some W which is not equal to 0, some subspace inside V, such that W intersect with the K is 0. So, but this is like, well, I guess maybe it's not the best way to write this argument. Essentially, what I want to show is that actually this is one-dimensional vector space. I know this is at least one-dimensional. I'm saying that, well, suppose this is not one-dimensional, suppose I have something else, right? So besides this K. But if it's just a vector space, so I can take something which is kind of in the complement to this K. But that's a contradiction to the fact that this is essential extension. Right? So it is not possible to find another W inside V such that the intersection with K is 0. Right? And if there are no such W, it means that if you, for example, try to construct the basis, you have a basic element for this K, and you try to find any other basic elements, that's just not possible. Hence, this is just a one-dimensional vector space. Okay. Okay, so finally, one of the two main theorems. So theorem that finishes the structure theory of injective modules over Noetherian rings. So let R be a Noetherian ring. So I is injective R module. So then we have two statements. So first, I is a direct sum of indecomposable injectives, and we know the structure for decomposable injectives. And 2, this decomposition is unique. And I can be even more precise. So this will be a direct sum of the injective halves of the R modulo P. So the number of summons of form injective half R modulo P depends only on I and P, but not on the particular decomposition, and is given by the formula. Dimension over the residue field of the home R localized at P, residue field I.
Yeah, do we know that there's there's only indecomposable injectives of the form like that, and there's no
Yes,
other?
we prove this.
No, we proved that this one is indecomposable.
Yes,
Did we prove that any indecomposable is of this form?
yes, we also prove this. I just proved the lemma, right? And then before that was this theorem, and before that was another theorem where we proved that if you have an injective, right, then you have
An element in this association.
yeah, so you have this thing as a direct summand, right? And since this is decomposable, there is no complement. So if decomposable has to be of the form of E of R modulo P. Okay. So the argument is for one is kind of set theoretic. So we consider set. So let S be all subsets of the set of indecomposable injectives. So indecomposable injective submodules of I, such that if I have large F in the set S, then the sum of all modules belonging to F is direct. So you can check this. I'm not going to do this. That this is partially ordered by inclusion. So this is by inclusion. So we apply Gauss lemma. So let's say this is F prime, and then we consider E, which will be direct sum of all J in the F prime. So this will be a submodule inside I. So since everything is injective, I can decompose I as a direct sum of the E and some complement. So let's call complement H in this situation. So if H is not equal to 0, so then there is prime ideal associated to the H, and hence I can embed the injective half of the R modulo P into the H. And I can make this F prime even larger, and f prime can be enlarged by injective hull of the R modulo P, which is a contradiction. So H is 0, and indeed, if you choose this f prime, this will be a decomposition of two into a direct sum of decomposables. Okay, that theoretic argument doesn't really show you anything, just a formal proof. But I don't think that you can do this better than this. Okay, 2. Let's say that I have this direct sum decomposition parameterized by some lambda in the set lambda. Well, let's do a computation. Hom over the localization Rp from the residue field to the localization IP. Well, first of all, direct sums commute with the localizations, so I can rewrite this as the Hom over Rp from the residue field to the direct sum over lambda of the I lambda localized at P. Oh, and this is just using that localizations commute with direct sums. Now I can also use that the residue field is finitely presented and pull out this direct sum. So I can write direct sum lambda in the large lambda of the Hom Rp K of P I lambda localized at P. Okay, so we know that this I lambda are all indecomposable injectives, so they are necessarily of the form injective hull of the R modulo some prime ideal Q. For any lambda we can find some such Q, so maybe I need to write something like Q depending on lambda, but for shortness of notation let me don't do this. So then, if I know this and I'm trying to understand this localization at the prime ideal P, well, since localization commutes with the taken injective hulls, I can take injective hull over the localization of the Rp modulo Q Rp, which is 0 if Q is not contained in the P. Okay. So if Q is contained in the P, then we take X, which is in the P, but not in the Q. And consider, so let phi as a map from the injective hull of the R modulo Q to the injective hull of the R modulo Q. So be multiplication on the element X. So just use this element X, induce an endomorphism of this module, which is just multiplication on X. Well, if I look at the kernel of the phi and intersect this with the R modulo Q, or by definition what it is, these are classes, say class with representative T, right, in the R modulo Q, such that X acting on this class, T plus Q, is equal to 0. But this is just 0, right? Because if this thing is 0, it means that the product of the X and T is in the Q. Q is a prime ideal, so I know that X is not in this prime ideal, so T has to be in this prime ideal, so this class is actually 0 to begin with. So this kernel intersection is R modulo Q is 0. and we have essential extension. So since we have essential extension, I can conclude that actually the kernel of phi is isomorphic to 0. So there is no kernel, so this phi is a monomorphism, and the image of phi is isomorphic to the injective half of the R modulo Q. So everything again injective, so this image is supposed to be a direct summand here, but this is indecomposable, so the only direct summand is this module itself. So since R modulo Q injective and indecomposable, the only possibility for this is that phi is an automorphism. Okay. So what we can say that in the situation where I have Q sitting inside P, but they not equal, right? And if I try to compute the home over Rp from the residue field K of P to the injective hull over the localization. No, wait. I already ever localized it. Well, wait, no. R mod Q. Do I need the localization here? So I'm trying to compute these dimensions. IP. Yeah, so it's originally supposed to be the localization, right? So I need to take this module and I need to then probably the best way to write this, maybe just to write P here. Yeah, but anyway, so it's well, I can rewrite this with the localization. It's not a problem. So it just I can take this thing and replace this with this thing. Anyway, so the point is that if in this situation I can take this home and write this as the home over the localization from the residue field to the x. So I want to multiply this by the x. Right? Since this is a multiplication on x is an automorphism, I can present any element from here as an x, something, an element from here. And of course, if I localize at P, if it was automorphism, it's still an automorphism. But now what I can see, if I look at these homes from the residue field, right? Well, it has one generator. It is sending this generator to something. And this something is of the form x times something. But x is in the maximal ideal. Is supposed to annihilate to what I'm sending this generator. So this whole home is just 0.
What if Q equal to P? Why it's still 0?
Well, I'm just eliminating. I'm computing this dimension, right?
Yeah.
And I eliminating the cases. I see
I
that.
understand.
So
But
if
in the last proposition, you say that if Q is proper in P, then this is 0. Why if Q is equal to P?
but I'm saying Q is proper. This is not equal.
Yeah, but what if Q equal to P? Isn't the same statement will say that this should be 0?
No.
Why? The question is about.
But because, for example, this part doesn't work. It's not possible to do this argument.
We take X, yeah.
Yeah. Yeah, so what I'm done, I'm trying to compute the Holmes, dimensions of the Holmes, or just Holmes, in what I have in this statement. And I eliminated the cases where Q is not sub-ideal in the P, then this is 0. And if Q is properly contained in the P, then the answer is still 0, 0. So the only possibility, when I have this, if I compute this Holmes, so I'll get only summons non-zero for lambda and the lambda 0. I'll define lambda 0 in a second. Hom R P, K of P, I lambda localized at P, and this will be K of P to the lambda 0. So where lambda 0 is defined as the lambda into lambda such that I lambda is isomorphic to the E modulo R P. Okay, so kind of three cases. In this case, we will get 0. In this case, we will get 0. And in the last case, which is case of the lambdas from here, we won't get 0. But all such Holmes I computed in the lemma before, and they were all one-dimensional. Hence, this answer. So you can see that no matter what decomposition you take, the number of direct sums of this form is kind of predicted by just the dimensions of the Holmes. So it doesn't depend really on the decomposition. Well, I'm out of time, so that's all for today. To prove this theorem.